Okay. Plan for today, it's hard. It will be hard. So I have 1.5 hours, and I will do 0 theorems and 0 proofs. I will be doing just definitions. So it will be crazy. I know how it sounds, 1.5 hours definitions. At my university, there is a professor who is saying that he cannot digest more than 3 definitions per hour. So I hope you will be better than the professors from my university, and you will digest all the definitions that will appear. I will try to do it as slow as possible, but please stop me whenever you don't understand something, whenever you need more examples or something is not clear. We have time, so don't worry. If you don't understand something, just say. So what we did yesterday, we said that a sequence of graphs, of growing orders sequence by Gn is converging if and only if for every graph, density of the graph in the sequence converges. If this you should remember from yesterday. One of the exercises is to show that you can do something a bit different. So instead of considering those densities, one can look at homomorphic density. So this is homomorphism density. And by that, I mean probability that if you take a random map from vertices of H to vertices of G, I will see a homomorphism. So it's probability that a random map from vertices of H to vertices of G is a homomorphism. What does it mean? Let me do an example. So density of cherries in a triangle was 0, right? However, I choose 3 vertices, I was not able to see a cherry. While this homomorphism density is not 0, because firstly, if I choose the 3 vertices are mapped to 3 different vertices, it's still a homomorphism. Every edge is still an edge, right? But moreover, if I map those 2 vertices to the same vertex and this one to a different one, it's still a homomorphism. Yeah, so out of all 3 cubed homomorphisms, what I need this guy to go wherever, and the remaining guys needs to go on any vertex which is not the same as the first one went, right? So it's 4/9. Here you understand the difference. Here we allow vertices being mapped to the same vertex, and also we don't care about non-edges. So what I want to say is that you get exactly the same theory if you say that a sequence of graphs of growing orders is convergent whenever those homomorphism densities converges. Yeah, so it's exactly the same theory. That's why in some publications or books, including Lova's book, you will not see this first definition, but the second definition. I'm working with this because it's useful for later applications that I will present you, but I want to say that it's really the same theory. I'm not saying, notice that for every H, if density of H converges, then homomorphism density of H converges. I'm saying if for every graph this converges, then for every graph this converges. Yeah, you see the difference. Okay, so this is one of the exercises to check. Okay, and what to plan for today? Today I'm going to define what's this flag algebra that appears in the title of the lectures. Flag algebras were defined by Rasborov something like 15 years ago, maybe. And this will be a so the algebra is defined on linear combinations of graphs. So let me say that curly G will be a class of graphs, of a set of all graphs. And on all those definitions that I will present today, I will be working in this set of graphs. But you can think that it's not necessarily you need to consider all of them. For example, we can define exactly the same in the class of triangle-free graphs, or K-form-free graphs, or graphs with colors on edges, or like lots of other discrete structures. Just to make the presentation easier, I will do it in the class of graphs. If you look at the Rasborov's original paper, it's extremely hard to digest because he's defining this for a model theory structure satisfying lots of different assumptions. And so it's harder to follow. I would be doing it for graphs. But really, think that you can do exactly the same for lots of other discrete structures. And with curly G with N, I will denote set of graphs on N vertices. Okay, so my goal is to define an algebra on linear combinations of graphs with real coefficients. Yeah, so elements here are just sum of some coefficient times some graph over some set of equations. Okay, and so let me define for a graph on W a function which goes from this to reals, and this function is just giving density with the same coefficients of those graphs in a graph. Yeah, so think about your favorite graphon, and this function, this homomorphism, is just giving me the densities of linear combination of those graphs in the graphon. Okay? What I want to do is show you some properties of those linear combination or those densities. First property will be the following. Note that if I take any graph in any graphon, I want to calculate this density. What it is? This is I'm choosing at random number of vertices H in a graphon W. I'm looking what's the probability that I will obtain exactly graph H, right? But I can do this random process in 2 steps. Instead of choosing immediately number of vertices of H, I can choose firstly some bigger set of vertices, let's say n vertices. Look at all possible graphs that I will obtain. Yeah, each with some probability. Okay, so firstly, what I'm doing, I'm looking at random n vertices in my graphon and looking what graphs it creates. Okay, and I look through all possible graphs that it can create. And in each case, I check what's the probability that in this graph I can find my graph edge. Yeah, so this is an equality. Why? Like, think about it as probabilities. So here I'm choosing edge vertices at random in W, and here I do the same process, but in 2 steps. First, choosing n vertices, and then among those n vertices, choosing vertices of edge. Yeah, and since I'm going through all possible options, each with its probability, I'm getting the equality. Yeah, you understand it? Okay, so what it means for my function? It means that wherever I take a graph and subtract this, so sum over all graphs on some number of vertices, I should maybe add here that n is equal to I, please. Those densities. And if I take the function on it, I get what? This is density of H in W here, and here I get some coefficients and density of G in W. So this is 0. Yep, this equality means that on any combinations of those, for every H and for every N at least side of H, this inequality, this element of those combination is just 0. Yeah, under this function F. Yep, it's clear. I haven't lost you yet. Good. So what I do, let me take space, linear space, generated by all those elements. Yeah, for every H and for every N at least size of A, order of H. If I take all the space, on this space, my function is 0. Yeah, so I want to do now, I want to define my algebra that I will work on as those linear combination of graphs, but factor out by this subspace. So what it means that now I not look at like those linear combinations, but linear combinations up to like adding, subtracting elements from here. Yeah, because there are 0 in my function. Let me do some example. If you calculate densities of edges in any graphon, I can do it in 2 steps. Yeah, as in the equality there. I can, let me go through all the graphs on 3 vertices. So I can have this, sharing for a triangle. And now in this empty graph, I cannot find any edge. Yeah, probability of finding edge is 0 there. Here I find an edge with probability 1/3. In a sharing with 2/3, and in a triangle with probability 1. Okay, so this is equality which is true for every graph on W. So in terms of my function, it means that I have the following equality. 1 of this plus 2/3 of cherry plus dry. Yeah, this is linear, so I can write it also like this. Okay. Those signs are too long. I'm too lazy to write them. I will be doing now some shorter notation. So since I'm factoring out this set where function f is 0, formally speaking, if I take an element from this, I should be writing a plus the characteristic class of the element a, right? Like, I mean, all of those combinations. I will be just writing a, and whenever I mean a, I mean it together with like adding or subtracting any linear combination of elements from this A0. Moreover, instead of writing all the time FW an element from A, I will be just writing A. So what I want to say is I will be writing equalities like this. Okay, F equals some linear combination of graphs. And what you should read by this is that for every graphon W, the densities of edges in a graphon W is the same as this linear combination of densities in this graphon W. Okay? Is it understandable? I will be using for the next 4 days this notation, so I hope you will understand it. For example, we have the Mantel theorem. Mantel theorem for graphs is saying that if graph is triangle free, then the number of edges is at most n square 1. Yep, this is a Mantel theorem. So how the Mantel theorem for graphons would look like in this notation? It means if the density of triangles in any graphon is 0, then density of edges in this graphon is at most half. Yep, because it's half times n choose 2 basically. Yep. So Mantel's theorem for graphons is just this line. And I will be proving those kinds of qualities. Probably you know, for example, Goodman theorem. It's just saying that if I take complete graph and color edges into 2 colors, then the number of monochromatic triangles is at least a quarter of all options, like quarter and just 3. Yeah, so in this language, it would be the density of triangles and density of complement of a triangle is at least quarter. Yeah. So in general, I will be translating graph theorems into graphon statements, and they will be looking like this. Some inequalities on graph densities, like densities of graphs in a graphon. Is it clear, everything now? Not clear? Okay. So in order to have algebra, according to the title, we need to have one more thing. We need to know how to multiply. Yeah, so now our goal is to define multiplication of those graph densities, or linear combination of graph density. What I would like to have from this multiplication, if I take two elements from my algebra, and go through this function, I would like to have that if I multiply two elements from the algebra, I obtain the same as multiplying the values of this one, right? So I would like to have to define this multiplication in such a way that this W, the function fw, still is a homomorphism. Okay, so how to do it? Let's think about it. What's this? This means? This means that I look at density of some graph in a graphon and multiply it by density of some other graph in a graphon. Yep. So it's a random process when I firstly choose H1 vertices in my graphon W and looking if it creates H1, and then looking at random H2 vertices and looking if it creates the graph W H2. So I want to do this process by choosing at random all the vertices. So H1 plus H2 vertices in W. So I sum up over all possible options, so over all graphs that I can obtain by choosing H1 plus H2 vertices. Yeah, I look at density of this graph in my graphon. And now what I should have here have this property. If you pick at random H1 plus H2 vertices, so now so I have a set of H1 plus H2 vertices, and now I would like to choose a random subset of H1 vertices and see if it creates H1 or not. Okay, so let me write here something that I will denote density of H1, H2, G, and by this I mean probability that H1 random vertices from this chosen set creates or induces H1, and the remaining one induces H2. Okay, let me do an example to see. So let's say I have H1 as an edge and H2 as non-edge. And now, here I go through all possible graphs on 4 vertices. So there are many of them. And for each of them, I look at the probability that among those 4 vertices, I can pick 2 and they create an edge, and the remaining two creates a non-edge. So I should write all possibilities. One edge, two edges, two edges, three edges. All edges. Have I lost something, or these are all the graphs on 4 vertices? Seems all. Okay, and for each of them, now I look at this probability. So whatever 2 vertices I will pick up here, I cannot see an edge. The probability is 0. Here, out of all 6 options, there is only one that is giving me an edge. And in this option, the remaining 2 vertices are giving me a non-edge. So it's fine, 1/6. Here, I have 2 options to pick an edge. And in both options, the remaining 2 vertices are not creating an edge. So I have 2/6. Here, what it would be? Yeah, 0, because I have 2 options to pick an edge, but the remaining 2 will not give me an edge, a non-edge as I need. Here is 0. Here, all possible options, all 3 possible options are giving me, that gives me an edge. The remaining 2 vertices are not connected, so it's 3/6. You agree? Here, this choice or this choice is not good for me, while this choice is fine. So it's 1/6. Here, all options, all 3 options of choosing an edge are good for me. So it's 3/6. Here, none of the options is fine. Those 2 are good. Yes, the complement is a non-edge. The vertical ones are not good, so it's 2/6. Here, only the diagonal edge is good for me. It's the 2 vertices picked at the random process. So it's 1/6. And here, whatever I will choose as an edge, the complement is not an edge. Okay, so I get equality of this type. Yeah, and you can check that it's really true for every graphon. Okay, and now this is a place where it matters that we are choosing it in a graphon, not in a graph on some big number of vertices. Why? Imagine now that I write the same quality, but not in a graph on W, but in some specific graph on 1 million vertices. Would it be true? What's the difference between those 2 things? So here, I'm choosing, let's say here, I'm choosing 4 vertices at random, and then among them 2 at random. Yeah, and the remaining 4. While on this side, I pick independent 2 vertices at random for H1, and independent 2 vertices at random for H2. So the difference between those 2 things is that in this process, I'm able to pick the same vertex twice. Yep. Here I'm choosing 4 different vertices. Here it's possible that I pick 2, and in this process I pick the same vertex. So in a graphon, probability of picking the same vertex in 2 random choices is 0. Yeah, I'm in the graph limit setting, so probability of picking the same vertex twice is 0. While for fixed graphs, like graphs on a fixed number of vertices, this would not be true. There will be some smaller order error there. Okay, and this is the reason why we are defining this algebra on graph limits, not on graphs on some fixed number of vertices. Okay. On fixed number of vertices graphs, this would not be true. There will be always some error term which will propagate if I continue calculation. In graph limit setting, this is a nice and true equality, and it defines me algebra of the space. Is it clear? Okay. There is some question in the chat. If it's clear, then we'll do it once again. But this time in a bit harder setting. I want to define everything once again. So those kind of inequalities, multiplication, in a setting where some of the vertices of my graph are fixed. So imagine once again, we started the whole lecture with defining what it means, density of a graph in some other graph. For example, what it means density of edges in a triangle, right? This is what we started with. Now I want to do similar thing, but define density of a partially labeled graph. So I have some vertices fixed. Think about it. I will denote it just by this unfilled circle. So density of such a graph in some other graph with fixed vertex. What it means? The fixed vertex needs to go to the fixed vertex, while all the other vertices are picked at random. Yeah, and I want to see if they create this graph. So for example, density of this thingy is like this vertex needs to go to specific chosen vertex in my graph, where this is at random. So this vertex can be chosen out of those two in random. Let's say that in this. So this guy goes here, and this guy is chosen at random among those two. And in one out of two options, I create this graph. Yeah, so this density is high. On another example, I look at this density of this edge with rooted vertex in some graph, for example, in K and N, with some vertex fixed. Yeah, so I have my complete bipartite graph, and one vertex here is chosen. So what's this density? I pick one vertex at random, anywhere here, and look at the probability that it will be connected with my chosen guy. Okay, so if it's here, then it's connected. If it's here, it's not. So the probability is among all remaining vertices in my graph, I need to be here. Yeah, you understand? In general, density of this thingy in a graph with some vertex D fixed. What's this? It's just the degree of this vertex divided by number of vertices in G minus 1. So 1 is 6. Yep. Okay. So we understand what it means. Of course, there can be more labels. For example, I can consider density of a root edge. And this is like looking on how many triangles my fixed edge is sitting. Yeah, so for example, here is half. Yep. Out of two options to pick up the random vertex, one option is giving me this graph. What I want to emphasize is that those vertices are labeled, are fixed. I should be writing here labels of the vertices so that you remember that 1 goes to 1, 2 goes to 2. I'm too lazy, as I already said. I won't be writing them, but you should remember that I keep the order. So the leftmost one is labeled with number 1. In particular, this is a different graph than this one. Yeah, because here I look at the probability that the random vertex is connected with the second labeled guy. And here I look at probability that the random vertex is connected to the first random guy, the first labeled guy. Configuration. Let me now be a bit more formal. So I fix some labeled graph. I will be denoting it by R and think about it as a root. Okay, let's say vertices R1 up to R. Okay. If I have a graphon, I also need to have like those chosen vertices, right? As in those definitions. So I have graphon W with chosen vertices such that I would write this as probability that x1 up to xk creates R is not 0. Oh, it's positive. What I mean by that, when I want to look at rooted edge, and for example, count how many triangles sitting on this rooted edge, I don't want to pick it in a graphon, which is, for example, complete bipartite, and pick two vertices here. Yeah, I cannot say about how many triangles are sitting on an edge if both vertices are not connected. Yeah. I'm not saying that they need to be connected because, as you remember, graphon may not have just zeros and one. Can be, for example, a random graph with probability half. Yeah. Here I can consider any two vertices. Probability that they are connected is positive, so I can consider the rooted edge in this setting. Okay, so I have graphon with those chosen vertices, and now I can define this density. So I consider a set of all graphs with labeled vertices. Some applications. Triangle and similar here, the same, but on the end vertices. Okay, and now I would like to define this function. It will be a bit more complicated, so let's erase it. Firstly, I will define this function because it depends where those xi's are. So we put it here. If for any age which is here, like it has those labeled vertices. And now what it is, it's the density that I obtain if those vertices forming R are chosen to be x1 up to xk. Yeah, and the remaining vertices are chosen at random. So it's probability that the W random graph of order of age is isomorphic to age. But now condition on the vertices R1 up to Rk being chosen to be those x's. Yes. And the graph formed by them. Okay, what it means? Say I have this random graphon, probability half everywhere, and I want to look at density of this thingy. So I have some vertices fixed, x1, x2. And this is probability that I will see my graph, but I already assume, so it's conditioned, that those two vertices are chosen to be x1 and x2, and that they are connected. So I look only at probability that the remaining vertex is connected with them. Yeah, so in this case, it's fw of x1, x2 will be just the probability squared, right? Because I need this guy to be anywhere, and always there is probability half to be connected with this vertex and probability half to be connected with this vertex. Yeah, I really don't care if on the probability that they are connected by an edge, because this is assumed here. Yeah. Is it clear? Let me do maybe more examples. We take a nice graphon. So I divide it in 1/3. One here, and the rest is zeros. So this graphon is something like a complete graph on 1/3 of the vertices and complete graph on the remaining 2/3 of vertices without any connections between them. Okay, and now what's view, if I pick 1, 6, and 1, 6, what's the density of this thing? Yeah, so this means that the two labeled vertices are mapped here, 1, 6, 1, 6. So they are in this first part. And now I want to look at probability that a random vertex is connected to both of them. Yeah, and any vertex in this 1/3 is connected to both of them. Any vertex here is not. So this is 1/3, right? While if I pick those vertices somewhere there, let's say 2/3, then now they are here in this part. I want to pick one vertex at random. If it's in the first part, it's not connected. If it's in the second part, it's connected. So I have probability 2/3. Yeah, you agree? Yeah, so this is denoting where the x1, x2 are going. So where those two vertices need to be. So what's your question? Oh, 1/3 is on the border, and I haven't wrote what exactly, what are the values on the border. Like this is any value less than 1/3, and yeah, and this is any value between 1/3 and 1. Okay, so if this is clear, I want to define what it means. This function defined for a root without explicitly saying where those x's goes. And by this, I mean just probability distribution of those functions. Yes, under a condition that they create this, the root. Okay, so what it means in this case? In this example, my root was two connected vertices, right? I take this graphon, and now what's this value? So it can have value 1/3, right? It can have a value 2/3, and with what probability? So we have value 1/3 whenever those two random guys are in the first part. What are the probability that they are in the first part? 1/9. What are the probability that they are in the second part? 4/9, exactly. But now I'm not writing that it's 1/3 with this probability and 2/3 with this probability, because I need to look at it under condition that they are creating this root. So what's the probability that two random vertices here are connected? Yeah, I need to have either both in the first part or both in the second part. So it's just sum of those two probabilities. Yeah, so I divide this by sum of the probabilities. So in other words, this probability distribution is 1/3 probability 1/5 and 2/3 with probability 4/5. Yeah, you understand? And this I can do for any root, any labeled graph. Let's do maybe one more example. Keep the same, but now let me take just single rooted vertex, and let's go for this degree. Yeah, so rooted edge, like one edge. What's this? If the vertex, the chosen vertex, is in the first part, then its degree is 1/3. Yeah, so it's 1/3 with probability 1/3. While if it's chosen here, then it's 2/3. And this is with probability 2/3. I was not dividing now by anything, because if I pick a vertex at random, it creates a vertex. I don't need to look at probability if it creates the root. Okay. So after those definitions, it's a good time to make a short break. If you haven't followed something or something is not clear, you can use the break and come to me, ask questions, and we will resume in, I don't know, 5 or 8 minutes. So we can proceed. There is one more thing I need to do. I need to define multiplication in this rooted set. Right? But firstly, previously we had this qualities of this type, right? That I can express density in a linear combination of larger densities. I can do exactly the same in this setting. So in general, it would be that if I have this graphon and the probability distribution with a given labels for any graph, I can just sum up over all graphs which are rooted and vertices as earlier, and this H, and look at density of H in G, and then this probability distribution of G. Yeah, if you want to think about it, it's exactly the same as we did earlier. Like for every possible choice of those roots, this is the density of the probability that the remaining random vertices are connected as in H, where this is this two-step process. Firstly, I'm picking the remaining vertices, like n minus order of r, the remaining random vertices, and among them, looking what's the density of G and what's the density of the fixed graph H, the graph H in graph G. And here both are with those labels, this root R. So I'm looking only at the remaining vertices at random. Yeah, and I can write it the same for every choice of placements of the roots. So for the density distributions, I also get the quality. Okay, so it's exactly the same as earlier. Do you want some example, or it's not needed? I need some interaction. If you want an example, let's say, let me take this. So my root would be just a single rooted vertex, and I look at degree of this vertex, or probability distribution of degrees, and this is the same as looking at all possible graphs that I can find on 3 vertices with 1 rooted. Okay, I don't write the remaining 2 because their density is 0. And now here, the one vertex can be chosen in 2 ways, and only one of them is giving me this graph. Similarly here, while here, whatever I choose is giving me a rooted edge, both here. Yeah. And if you want to check really whatever graph or graphon you will take, then degree of the vertex is just this linear combination of probabilities finding those graphs. Okay. Now we need to do the multiplication. So similarly as before, I want to define multiplication. Let me do it already like this. I want to multiply 2 graphs. They are rooted, so they are this GR. And as before, it will be sum over all possible options. But now, here I'm choosing at random order of H1 minus order of R vertices, right? Because those vertices are fixed, and those needs to be chosen at random. Similarly, here I need to choose order of H2 minus order of R. So how many vertices I need to choose here? I need to choose among the rooted vertices H1 plus H2 minus order of R. Yeah, like here also I have R vertices which are fixed, and the remaining H1 plus H2 minus 2R will be those random ones. And among all such choices, I look at the density similarly as before. I will write it and then explain. So it's density probability that among random H1 minus order HR vertices of G together with the vertex with those labels creates H1, right? And the remaining H2 minus R vertices with R creates H2. It's exactly as before. The only difference is that the root is fixed in every graph here, in G, and in the graph on the day, doing these computations. Let's do some examples. Let's say I want to multiply degree times degree. Okay. I go through all graphs which are having 2 random vertices and the root as always. Okay. And for each such graph, I look at probability that first, like the random chosen vertex will be connected to the root, and the remaining vertex also connected to roots. So here I have just two options, either this or this, right? And whatever vertex I will pick here, it's connected. Whatever vertex I will pick here, it's connected. And the remaining one is also. So the coefficients are 1. Different example is this multiplication. So here I have degree times non-degree of this fixed vertex. So now I need to have also 3. And I need to have one which is connected and one which is not. There are two possible options. Okay. And what's the coefficient? Is the probability that if I, among those two vertices, pick one at random, I will see the first graph. Okay, so it can happen with probability half. And the remaining vertex is creating this satisfied. Yeah, similarly here. I need to choose one vertex at random, and I have probability half that it will be an edge, and the remaining vertex is not connected. Is it clear? Or more examples? No, you're clever. You don't need more examples. Okay. Maybe let me do one more example to emphasize the thing that I said earlier. The order of these rooted vertices matters. Okay, for example, if I multiply those two things, I will have two random vertices, and I need in this graph that the random vertex is connected with the second root, and here that the random vertex is connected with the first root. So to have non-zero probability, I need to have such a matching, and between them there can be an edge or not. And here, what's the probability that a randomly chosen vertex among those two is connected with exactly the second one? Yeah. So if I choose this one, it's not connected with the second root. If I choose this one, it is. So this is with probability half. Similarly here. Yeah, you understand? I want to emphasize that this is really different graph. Yes, and if I connect them not like this, but differently. Yes, so really, I look at probability here that the random vertex out of those two is connected with the second guy. So you really need to choose this. Okay. So what we have now, we know how to multiply. We have equalities of this kind. So we can define the algebra as before. So as before, I take A0 with labeled root as linear space generated by all kinds of those qualities. So H minus. And then define my algebra as just all linear combinations of the graphs with labeled roots divided by this subspace. Yeah, so I identify all elements of the algebra if they differ by elements from this subspace. Okay, and this algebra with the multiplication defined here. Oh, this I define for multiplying graphs, but by linearity you can extend it to the whole space, right? So with this algebra, with this multiplication, create an algebra, and this algebra is called exact flag algebra by Lansborough, and this is the main topic of those lecture series. I got a question, why it's called flag algebra? So the reason is funny, it's just how it looks. If I draw you this thingy, so I have vertex which is rooted, it's fixed, it's on the ground, I cannot move it. And this guy is just waving around and like a flag on a wind. So that's why it's called flag algebra. Okay, good. We managed to define the main thing of the lecture after an hour and a half, like 2 hours and a half of lectures. I have a few more minutes, so let me do one more thing that will be useful. Are there some questions? Yeah. Oh, yes. Algebra with fixed root. Thanks. If you know, for example, degree distribution of your graph or degree distribution of your graphon, so you know all the elements of your algebra with a fixed root, then you can say what's the, for example, edge density, right? If you know distribution of degrees, you know what's the edge density. So in other words, there should be a way to translate, like to go from this algebra with some roots to algebra without roots. Yeah, we should have some operator which is behaving like averaging over all possible choices of the root. And this is what I want to define. Yeah, like intuitively. If you know degree of every vertex, if you average it, so sum up over all vertices and divide by n, you get the average degree, which is basically the edge density, right? So this is what we want to do. This operator, like averaging operator, is denoted by such double parentheses. And what we want from it, we want that if I take any element from my algebra and a graphon which has positive density. So, I mean, there is a chance of finding R in the graphon. Oh, maybe I should do it. Okay. This is labeled. So by R0, I mean R without labels. Yeah, so just as a graph, not labeled graph. So what I would like this to behave like averaging over all possible choices. So what I would like to have is that if I calculate this density after averaging, I get basically the expected density with rows multiplied by density after I of the root. Average roots. What do I mean by that? If I tell you what's your distribution of this, so I can tell you what's the number of triangles sitting on every edge. Then you could translate, you know what's the density of triangles if you also know what's the density of edges. right? If you know the density of edges, like number of edges, you know how many triangles are sitting on every edge, you know what's the number of triangles in your graph. Yeah, so this is like this. I look at number of edges, so all possible placements of the root. I average on this, so average over the number of triangles sitting on every edge, and this should give me the density of unrooted triangles, so just the density of triangles. Yeah, this is what I would like to achieve. And how to do it? Let me define parameter. So my H is a rooted graph. So rooted graph, let H0 be as here, just H without labels. So just forget where were the labels. And I want to define this parameter Q of a labeled graph to be the probability that choosing the vertices are, so the labels at random in the graph H0. So I have a graph without labels, I'm choosing labels at random, and I'm looking at the probability that I will create exactly H. Let me do some examples. So this is one. I take an edge and now pick label at random, either here or here, and I look if it creates this guy. So wherever I will put the label, it will be this graph, right? So here is one. While, for example, this. I have a cherry. I choose at random one label, vertex. And if I choose it here, it's not this graph. While if I choose it here or here, it's this graph. So it's 2/3. Yeah. Okay, so one last example. It's got two labels. Okay, and now what it will be? So in a graph which consists of just one edge of three vertices, I need to choose two labels. And I need to have that the first one is connected with the remaining vertex and the second one is not connected. Yes, for the second one, I have only one choice out of three. And for the first one, I can pick any of those remaining. So it's 1/3. Yep. Okay. And I want to define this averaging of a rooted graph by this coefficient multiplied just by the density of H0. Yeah, so in other words, looking back to these examples, averaging of a degree, a rooted edge, would be just edge density. Yeah, I remove the labels and multiply by the coefficient. Averaging this thingy will give me 2/3 cherries, while averaging the last example will give me 1/3 of this complement of a cherry. Yep. Okay, maybe quickly why this definition is good. To be formal, what's the right-hand side? For a single graph. So the density of H in W with fixed roots, this was this big integral, right? So I was integrating over all vertices in 0, 1, and then looking for the probability that they're connected, Bj of J, and then look at J, and that they are not connected. Yeah, I'm not writing the equality. But this was conditioned that the remaining vertices are creating R, right? So if I would like to write just this part, I would write here without edges in R. Yeah, and edges not in R. But this density is exactly this integral for those remaining vertices. So together I can write this, but there is this small factor. If I pick at random all the vertices from H minus R, and I need to divide by the size of the automorphism. Yeah, so formally speaking, this is this integration. And if you want to write it in terms of density of this graph, yeah, so for getting the regions, then I have exactly that integration, but with a different factor here, right? If you remember, it was just the size of H divided by the size of its automorphism factor, size of order of H factorial divided by size of the automorphism. So now I have automorphism with H0 divided by order H0, which is the same as order of H. Okay, so I obtain something like this. And now you can see and check by yourself that it's really this coefficient that we just defined. It's exactly the probability that if I pick at random vertices from H without choosing vertices from the root, I will obtain the graph which is H. Yeah, so it's exactly this coefficient. Yeah, so it satisfies exactly what we want. Yeah? We get that this is density of the root of this average H. Okay, so now we know what's algebra of rooted graphs, we know algebra for unrooted graphs, and we know how to translate from one to the another. Let me just do one more quick notation remark. Whenever I will be writing an element of this algebra and some real number, I will be sometimes writing, for example, a at least x, or let's say degree at least 1/8. And what does it mean? I mean that in the graphon I'm considering now, for every placement of the root, the degree is at least 1/8. Yeah, so basically, by this I mean that this distribution is at least this value. Yeah, it will be just quicker to write it like this. Yeah, of course, I can write it only when density of unrooted R in my graphon is positive. Since this is linear operator, if I have this inequality, in particular, if I have A is at least 0, then it implies that after averaging, I have also at least 0. Yeah, because it's just linear operator. Yep. Yes, here. Thank you. Okay, and similarly, if something is 0, for example, on every edge I have no triangles, then it implies that after averaging, the density is 0. So this implies that the density of triangles is 0. Right? You agree? If I don't have triangles sitting on any edge, or this is probability distribution. So with probability 1, I have no triangles sitting on the edge. Then I have density 0 of triangles. And more generally, if density of this probability distribution is equal to some value, then after averaging, I get this value, but multiplied by the root. Yeah, so if triangle density, like on every triangle I have, let's say, quarter proportion of triangles, then after averaging I have quarter, like density of triangles is quarter times density of edges. Yep. Okay, so this, thanks to this notation, I will be writing some inequalities and equalities in a quick and short way. Okay, so this ends this most technical and full of definitions lecture. Next day, tomorrow, will be the funniest lecture out of those 5, because we'll be doing just examples. We'll be proving Mantel, proving other theorems, and it will be more fun. So I hope you are able to digest the definitions that will appear today. Tomorrow we'll try to use them in applications. So tomorrow will be funnier, I promise. Thank you.